Unit 3, Lesson 6, the inverse of a quadratic. So we know that if you're given a parabola, the inverse is not a function, and that's because many of the inputs have more than one output. So we have learned that we need to restrict the domain of f at x, that the inverse is a function. So if you're given a parabola and you're asked to find the inverse, it's very important that the parabola is in vertex form, okay? And this is because it makes the process doable, okay? If your function was in standard form like this, so if you were asked to find the inverse of this quadratic, it would be very difficult because the first step is to switch the x and y's, and then you couldn't isolate for y because you can't combine 2y squared plus 7y. They're not like terms. Okay, so it's very important that your equation is in vertex form before you try and calculate the inverse. Okay, so we have a quadratic in standard form and we're asked to find the inverse. So first thing we need to do is we need to make sure that our quadratic is in vertex form. So to go from standard to vertex form, we need to complete the square. So let's go ahead and do that. Okay, so by completing the square, we now have our quadratic written in vertex form, so we can now find the inverse. So to find the inverse, we want to set h at x equal to y. And then we switch our x and y values. And then we use samdeb to isolate for y. Okay, and after isolating for y, we have come up with our inverse. Just remember, it is very important that you follow samdeb in order to isolate for y. Okay, example 2, we're given a quadratic, and we are asked to graph both f at x and the inverse of f at x. So to graph f at x, we know it's a quadratic, so let's start with our base equation. And then our transformations tell us that we must move to the right 1 and up 2 units. Okay, so the red graph is our fully transformed graph. Okay, now we need to graph the inverse, okay? And the way we're going to do that is we're going to set a table of values up, okay? And this table of values is going to be for f at x, so the completely transformed graph, so that red graph. Okay, so the points there from the graph, starting from left to right, -1 and 6, 0 and 3, 1 and 2, 2 and 3, and 3 and 6. Okay, so now to figure out the points of the inverse function, we're just going to flip our x and y values. This is now 6 and -1 instead of -1 and 6. Okay, and let's plot those points on the graph. And there's our inverse function. So is the inverse a function? Okay, and your answer is no, because it would not pass the vertical line test. Okay, and also, most of the inputs have more than one output. How much of our original graph, so the red graph, do we need to discard, or do we need to restrict, so that the inverse is a function? Okay, and basically we can just restrict our original function to half of it. Okay, if we pick this half only, then if we were to graph the inverse, it would be just this half. And that would be a function. Every input has one output and it would pass the vertical line test. Likewise, if you wanted to restrict the original function to just that half, then your inverse would be just this line, and it also would be a function. Part D, restrict the domain of f at x so that the inverse is a function. So we just add in that restriction piece. So the domain of f at x has to be restricted such that x is less than or equal to 1, or you could write x is greater or equal to 1. Then the inverse would be a function. Okay, and part E we already did on the graph. Example 3, determine the inverse of the function given there. Okay, and obviously we have to state this restriction to show that the inverse can be a function. So I'm going to take f at x, replace f at x with y, and then switch x and y. I'm going to isolate for y. Okay, so there's your inverse function. Okay, example 4 is an application question. So the profit in thousands of dollars on the sale of jeans can be modeled by the function p at x equals negative 8x squared plus 72x minus 112, where x is the number of pairs of jeans produced in thousands. So that's important to remember for final therefore statements. Part A, how many pairs of jeans would they need to produce in order to maximize profit? So when you see the word maximize, you want to think the vertex of a quadratic, right? Because the vertex of a quadratic represents the maximum value. So to solve part A, we need to figure out the coordinates of the vertex. So our function is this. And it's very hard to determine the vertex from a function in standard form. So let's put this function into vertex form by completing the square. So now that our equation is in vertex form, we know that the vertex is at 9 over 2 and 50. Our x value is 9 over 2, which is 4.5, and our y value is 50. So that would mean that this value is 4.5 and this value is 50. So if the question is asking us how many pairs of jeans do they need to produce in order to maximize profit? Okay, if the x-axis represents the number of jeans and the y-axis represents profit, which of those two values, the 4.5 or the 50, represents the number of jeans that maximizes the profit? Okay, hopefully you came up with 4.5, right? Because the way we read this point is that if you produce this many jeans, you will gain the maximum amount of profit possible. So to answer part A, and remember this is a number in thousands, so it's not 4.5, it's actually 4,500, we would say, therefore, to maximize profit, you must sell 4,500 jeans. Okay, part B, find the inverse and then explain what it means. So let's go ahead and take our equation in vertex form, because remember, to find the inverse, you must start with a quadratic in vertex form. And I'm going to replace p at x with y, and then I'm going to switch x and y. And then I'm going to isolate for y. Okay, so that's the inverse equation. Now we have to explain what this inverse equation means. To do that, we're going to look at the wording of the original question and pay close attention to what each variable represents. So in P at x, so not the inverse, just in regular P at x represents the number of genes and P at x is the profit. Okay, so this equation is set up such that if you plug in the number of genes as your input, your x value, this equation outputs or tells you what your profit is going to be. Now in the inverse, it's going to be switched. Instead of plugging in number of genes as your input and then getting your profit, which is the output, it's going to be the opposite. You're going to plug in the profit as your input and output number of genes. Okay? So the inverse function would tell you how many pairs of genes you would have to produce in order to get a certain profit. So if I said, I want to make a profit of $1,000 one day, how many genes do I need to produce? I would want to use my inverse function. I'd plug in 1,000 for X, and then it would output the number of genes I need to produce in order to make that $1,000 profit. Now some of you might be thinking, well, I can figure that same information out from P at X. I don't need my inverse function to figure that out, right? You would just plug in 1,000 for profit, and then solve for X to figure out how many genes you need to sell to get that profit of $1,000. And that's fine, you can still do it that way. But plugging in 1,000 into this equation to figure out the profit is way easier than plugging in 1,000 into this equation and solving for X. Because over here, to solve for X, you're going to have to factor that. And that's going to take a while. Down here, if you plug in 1,000, you just have to do the math. And then you know what, and then you've solved your question. Okay, so both processes will get you to the same solution, but it's a lot easier to use the inverse.